I recently came across this question that I thought was interesting enough to make a video about it. So the question says, how can we evolve a density matrix ρ or a quantum circuit with a unitary U that has actually been implemented in real hardware? So we know that mathematically, an evolved density matrix is given by U dagger ρ U. But if we're implementing this U in real quantum hardware, well, this is not going to be an exact unitary. It's going to be some noisy unitary. So it's going to be a quantum channel that might be very difficult to characterize. So ideally, what we want to do is initialize our circuit to use this state ρ and then evolve it through the actual hardware. Well, if ρ is a pure state, this is simple enough, right? Because for a pure state, ρ is given by the outer product of some state psi with itself. So all we need to do for this density matrix is to initialize the all zero state to our state psi and then run it through our quantum circuit in real hardware and then measure it to collect statistics about the behavior of the overall evolved system. But what if the state is mixed? What can we do in that particular case? How do we initialize this state? Because the problem here is that when we actually have quantum hardware, the way we manipulate qubits is with unitary operations. And a mixed state is a combination or an ensemble of pure states with some classical probabilities of occurrence. So one possible way to do this is by using purification. And we briefly talk about this in another video. But the idea behind this is that if we expand our system to not only have the number of qubits associated with ρ, but we add some additional part of it, so more qubits, for example, then we can find some state psi sub SA for which if we trace out the additional added system A, then we get ρ. So here, basically what we're doing is this psi sub SA now belongs to the Hilbert space of our original system to which ρ belonged to, and then some additional Hilbert space that we're adding to it, right? And this works well. There's a procedure we can follow to find this psi sub SA. But the problem is that we need to add qubits to make this work, right? And every time we add a qubit, we're basically doubling the size of our space, which if we already have a big system to begin with, could be complicated. So another idea that I had was, well, what if instead of using purification, we looked into the spectral decomposition of the matrix ρ? So since ρ is a positive semi-definite operator, it will have a spectral decomposition with eigenvalues lambda sub I that are actually real. So here what we have is the sum of the outer product of this orthonormal states psi sub I that form a basis pre-multiplied by some lambda sub i's that, if they're always positive, can be interpreted as classical probabilities of finding the state ρ in the state psi sub I. So basically, we have an ensemble of state psi sub i's with probability of occurrence lambda sub I. So then, if we can find the psi sub i's, what we can do is we can prepare a circuit of the following form, where now we initialize, for example, the state psi 0 and evolve through the unitary U that is in real hardware. Then we can do the exact same thing for psi sub 1 and then all the way down to psi sub n. And then once we have implemented the circuits, what we can do is sample from each one of these with the probabilities lambda sub 0, lambda sub 1, lambda sub n. So basically, if, for example, the first state, psi sub 0, has a lambda sub I of, let's say, 0.1, then we would sample out of all the circuits with a probability of 10% of picking this circuit through all the different shots that we're going to take when we run this through real hardware. So if, for example, we're going to execute our system with, let's say, 1,000 shots, then for this first shot, we sample from the circuits, pick one with its associated probability of occurrence, run the simulation, then pick the next circuit, which is going to probably have a different probability of occurrence, run it through real hardware, and if we have enough shots, then we can have enough statistical significance to say that we evolved that matrix rho, which was for a mixed state, over our unitary and obtain the results. So just to start with a simple example of what we mean by performing the spectral decomposition, let's look at, for example, a density matrix given by the state 0, 0 and the state minus, minus, in which we have a classical probability of occurrence of 1/3 for the state 0, 0 and 2/3 for the state minus. And then this is obviously not in a spectral decomposition form because the state 0 and the state minus are not orthonormal, right? So what we can do is, construct the matrix for this and perform the spectral decomposition, which is going to give us a different state psi 0 and psi 1, with some different probabilities of occurrence, lambda sub 0, lambda sub 1. So, instead of trying to find this manually by, finding the eigenvectors and eigenvalues of this matrix, let's go ahead and implement this in Python to see how this will work. So first we're going to import numpy, sympy, and a density matrix class from Qiskit to make our lives easier. And then let's generate that matrix we just looked into. So basically, with probability of 1/3, we have state 0, and with probability of 2/3, we have state minus. And then if we display that matrix, we have what we had shown before. And then we can simply just find the eigenvectors. So let's call them our lambdas, and our eigenvalues, let's call them our psi's, by using this linear algebra function from numpy that computes the eigenvalues and eigenvectors if we pass a given matrix. And then if we display, let's say, our eigenvalues, our lambdas, we get these two values, which, if we did it correctly, they should add up to 1, because as we said, we should be able to interpret them as classical probabilities of finding the state rho in either phi sub 0 or phi sub 1. So, if we do our lambdas and we sum over them, that should be equal to 1. So it's pretty much 1, just we don't get exactly 1 due to some rounding errors. And then if we display our eigenvalues, so our psi's, we have here in the columns of this matrix each of the two associated states with each of the lambdas. So if we go back here, what we would have for our spectral decomposition will be a rho equal to 0.872 times the state 0.850 minus 0.521 plus 0.127 times 0.520 plus 0.851. So here, this is our lambda 0, this is our lambda 1, and this is our psi 0, and this is our psi 1. What we're missing here to complete the density matrix will be, the complex conjugate of psi 0 here and the complex conjugate of psi 1 here, right? So that will complete that matrix. Now, if we did this correctly, what we should be able to do is to reconstruct this original matrix by doing this summation we just showed here, right? So let's go ahead and try to do that. So let's again copy and paste this decomposition to get our lambdas and our psi's. And here I'm going to assign the psi's now as the transpose of what we get here, because the way this function in numpy returns our state vectors is in the columns of this matrix, and it just makes it easier for me if now they're in the rows of a matrix. And then what we can do is a for loop where we're going to iterate over each of our eigenvectors. And if this is the first time we're looping through them, we're going to assign our value to, let's call it row recon for reconstructed. And then we have to take a lambda I times the density matrix of whichever state we're in our list of size that we're iterating through, right? And if it's not the first occurrence, what we're going to do is just going to add the next one to this first summand of our density matrix. So then I'm going to do plus equal and just basically the same, right? Okay, and if we reconstructed that correctly, it should match the original row we had here above, right? So here we had this 2/3 minus 1/3 minus 1/3 1/3. So let's just display both that original matrix and the reconstructed matrix. And here I forgot to put it in, and here I used states instead of state. And here we have it. So our original matrix and our reconstructed matrix are identical, which means that this decomposition works well. So let's now go ahead and use this method we have described to run a density matrix through real hardware, right? So I'm going to do a few more imports here. So I'm going to import from Qiskit a quantum circuit, so we can construct the circuit we're going to evolve our density matrix through. And this transpile function that takes our quantum circuit and transpiles it into the gate set that is used by the real quantum computer to run the circuit. And then I'm going to import this density matrix function so we can, instead of using this simple one, we can use a random density matrix and see that this works in general for any matrix we have. And then this plot histogram to plot the results. And then to run our simulations first before we run it in real hardware, I'm importing this air simulator from Qiskit Air. Okay, so let's go ahead and create some random density matrix. And let's do it for 3 qubits. So that way we have big enough of a system to make this interesting. And let's perform that same decomposition we showed above. So we're going to get some lambdas and some size, and we're going to transpose the size. So the state vectors are in the rows of a matrix and not in the columns. And let's reconstruct that matrix. And then as a sanity check, let's just print both of those to see if our randomly generated density matrix matches the reconstructed density matrix. So here we have it. It's a completely random density matrix, and the reconstructed one looks exactly identical. You can look into it carefully if you want and make sure that it does indeed match. So here we have an 8x8 matrix because we have a total of 3 qubits. Okay, so now let's go ahead and create some circuit that we want to evolve this density matrix through. So for this example, I'm just going to use a GHZ circuit. So here I have a function where I define the particular circuit, and here we can just, take a look and see if it's doing it correctly. So let's define a quantum circuit for, let's say right now 3 qubits, and let's just draw that and see if it works correctly. So here we have it. If I increase it to 5, it should generate a GHZ circuit for whatever number of qubits I'm passing. So here, since I define a variable n here to make this general, I'm just going to pass n here as well. And now we're going to evolve our density matrix through that quantum circuit. So what we're doing here is basically having Qiskit evolve this using just matrix multiplication. So as we describe here above, all that is going to happen is we're going to get an evolved density matrix where we're multiplying by the transpose conjugate of that circuit. So this QC has a U associated with it, and then rho, and then that U again. So this is the ideal scenario. We're evolving our density matrix, our random density matrix, through this quantum circuit. And then what we can do here is, well, we could display it, but that's not gonna tell us much about it, right? It's a random density matrix evolved through that quantum circuit. So what is interesting is to actually sample from this density matrix as if we were performing measurements. So let's call this, let's actually define first some number of samples. So let's do 4096, and then let's call this qinfo counts. And I'm calling it qinfo because I'm doing all of this using the quantum info package from Qiskit to get this results. And then all we need to do is take that evolved density matrix, and we can use this sample counts method to get a distribution. And then after that, we can plot that in a histogram, and this is the result we get. So basically all we've done so far is we generated a random density matrix, we evolved it through this GHZ circuit, and this has all been done, through matrix multiplication, nothing crazy going on here. And then from that evolved density matrix, we just sampled results as if we were making measurements on that evolved state. So what we want to do next is run an actual simulation as if we were running this through real hardware and compare the results to see if this idea of sampling from quantum circuits that have been initialized using the spectral decomposition of our density matrix holds or not. So let's do that next. So let's go ahead and create an empty list where we're going to store the circuits for each of the different initializations of our eigenvectors. So now let's create a for loop where we're going over each of the states in our decomposition. And then we're going to create a quantum circuit with n qubits and n classical bits, because now we're going to be performing measurements. And then we're going to initialize our quantum circuit to each of the states we are iterating over. And then once it's initialized, we have to add the circuit we want to evolve this state through. So we said this was going to be our GHZ generating circuit. So we're going to add that to this circuit we're constructing in all of our qubits. And here we're going to set this in place to true, so it gets added to the circuit we're already working with. Then I'm going to just add a barrier here before our measurement blocks. And then we're going to do measure all our qubits, send to all our classical bits. And then I'm going to display each of these circuits by doing qc.draw. And lastly, I'm going to append each of the circuits to this list, this empty list we created up here, so we can then run this through the simulator. So if we execute this, we can see here that we have our circuit initializing the state in size 0 and then running it through the circuit we're interested in and performing measurements. Then this will be psi 1, psi 2, psi 3, psi 4, psi 5, psi 6, psi 7. So from 0 to 7, we have a total of 8 circuits because our density matrix is an 8 by 8 matrix, and we perform the spectral decomposition. We're going to have a total of 8 different possible states in that decomposition. So now let's run this through a simulator. So we're going to define our backend as air simulator, and I'm going to create another empty list where we're going to store our transpile circuits. So we need, as we said before, we need to transpile our circuits before running them. So all I'm doing here is just going over the original list we had. So here we define that list circuits, right? And transpiling each one of these and then storing it in another list. All right. And now what we need to do is to run this simulation. We said that we need to sample from each of these 8 circuits using our lambdas as the probability of occurrence of each of the circuits coming out of our sampling, right? So the way we're going to do this is, instead of creating a really large list of circuits where we have sample from this, I'm just going to create a list of indices which are going to represent each of these circuits. And every time we have, let's say, index 0, that means we're going to run circuit 0. If we have index 5, we're going to run circuit 5, and so on. So I'm going to create this list of indices by using this NumPy random choice function. And here, since we have 8 circuits, I'm going to sample from the numbers 0 through 8. And the size of this list of indices is going to be the number of samples or the number of shots that we want to run this whole circuit. And we had already defined that up here when we run the ideal simulation, in which we evolve our density matrix just using matrix multiplication. And then lastly, what I need to pass to this choice function is the probabilities associated with each of the 8 different circuits. So here I'm going to have to pass the lambdas that we found from our spectral decomposition. Now, before doing this, one thing I want to show is that if we look at these lambdas, they're complex numbers. But as we said, since density matrices are positive semi-definite, these lambdas should always be positive real numbers. So if you see the complex part of these numbers, it's just very, very close to 0. These are just approximation errors during the decomposition procedure in NumPy. So all I'm going to do here is just make sure that I'm only taking the real part of those lambdas, so this doesn't throw an error. All right, and if I print this, we're just gonna get a list of indices from 0 through 7, where each of those has been sampled with the probabilities given by this lambda array. So the probability of sampling circuit 0 is 0.35. The probability of sampling the second circuit is 0.0004, and so on. And now for the simulation, what I'm going to do is I'm just going to iterate over each of these indices and run a simulation using this run method for the circuit or transpile circuit associated with that given index. But I'm only going to do it for one shot because this indices list is the size of the total number of samples that we want to run our complete system through. So we already have, these indices are already the 4,096 shots that we want to execute. So here we're iterating 4,096 times, sampling a circuit corresponding to this list of indices, and then executing the circuit only once. And then I'm going to set this memory here to true. So what this is going to do is, instead of giving me, in Qiskit, when we run this type of simulations, you get a dictionary with the labels of the measured states as a key and the total numbers we measure that state as the values. But since I'm running here different circuits, what I want to do is actually get a list with each of the states we have measured. So that's what this memory allows me to do. And then here I'm going to extract the result, and then I'm going to set here output equal to result.getMemory. And I'm going to run this quickly and basically just print this output. But let me just do this for a smaller example so we can see what's going on. So instead of the whole 4,096 list of indices, I'm just going to do here 0, 1, 1, 3, 4. So this will run circuit 0, then circuit 1, then circuit 1, circuit 3, circuit 4. And I just want to show what the outputs of this simulation looks like. So here, since we're running only one shot, the first simulation, which was running circuit 0, gave us this result. The next simulation, which would run circuit 1, gave us 100. The next one also gave us 100, and then last one gave us 000. So each of these simulations is giving us just one outcome, and that's why I use this get memory, because if we use here get counts, which is the typical way of doing this in Qiskit, what we're getting here is dictionaries with those keys and just a value of 1. So it was easier just to do here get memory and then initialize a dictionary for every possible key, so every possible number from 000 to 111, and then accumulate the results there. And again, the reason I have to do all this is because we're running different circuits, which would give me separate dictionaries every time I execute the simulation, which were hard to combine. And here, all I'm doing then is just creating my own dictionary and adding up the results for every time we execute the circuit. So then let's go back here to iterating over the actual indices, fix this typo here. And now let's go ahead and compare the results that we got from running the ideal simulation using the quantum info package and this simulation in which we have sampled over all these different circuits that came from the spectral decomposition of our input density matrix. And if we see here, the results actually are very similar to each other. And we can go back up here and rerun this so we get a completely different density matrix. Run all the cells again. And here we can see that the results are different, but for the ideal simulation and our quantum info simulation, the results are very similar to each other. All right, so the final step is to actually run this in real hardware. For that, we're going to have to import a couple more things. So we're going to import the IBM provider and this function least busy. So we can pick the quantum processor that has the smaller number of people waiting in queue. And then this job monitor just to see how the execution is going. So we do those imports, and then what I'm going to do here is just pick our quantum processor based on whichever is the least busy and has, 5 qubits at least, so we can execute our circuit. So this takes a little bit of time, but then this should print the name of the QPU we're gonna be using. So here we see we're gonna use Manila. And then what we need to do next is transpile our circuits again, but now using the QPU as the backend instead of the simulator. And I'm going to display those circuits just for you to see that this is actually turning that initialization block of the state into gates. So here we can see all the 8 circuits that we're generating for each of our 8 possible executions. And then what I'm going to do next is slightly different than what we did above. So above, we created a list of indices and we sampled each of the circuits based on whatever we had in that index. And then we run a total of 4,096 simulations only with one shot. But I can't do that in real hardware because that would mean that I need to execute a total of 4,096 separate jobs, which would take an incredible amount of time. So what I'm going to do here is actually define, the number of shots as the same as what we had before, so 4,096. And I'm going to have the QPU, or the quantum processing unit, run the whole list of circuits with that number of shots. So all of these 8 circuits will be executed with this total number of shots. So then the problem is that we won't be able to combine all of those results because some of the circuits have a larger probability of occurrence than others. So what we'll do is we'll truncate the list of the results of each circuit according to the probability associated with each of the circuits occurring. And that should give us a good representation of what we're trying to accomplish. So then here I'm just going to get the job ID assigned to this execution and print it. So now our circuit is being executed in real hardware. And here we can look at the status of it, which it says has been queued. And this is going to take quite some time. So we can go here to the IBM Quantum Platform website, and we can see that our job is now queued. So we're gonna pause the video here and wait for this to complete to keep going. All right, so now that job is completed, so we can go back here to where we had left our job queued, and we can extract the results by doing job.results. And as I mentioned before, since we run each of the circuits for 4,096 shots, what we need to do is just take the total list of results of each of those circuits and trim down the number of items in each of those results by a weighted value given by the probability of sampling each of the circuits. So what we're doing here is we're doing a for loop where we're going through each of the 8 circuits we run, extracting the sample results that we run in our quantum processing unit, then deciding how many samples we need from each of these circuits, which is basically the total number of shots weighted by the probability of having that circuit. And then we're adding that to a list that has all the samples that we have accumulated. So we run that. And then what we're doing here is now taking that list of samples and just turning it into a dictionary so we can compare the results with those of the simulations we run above with the quantum info package and the simulator where we did exactly the same thing we had done here with real hardware. So let's run that too, and then let's compare all the results here. So for real quantum hardware, for the air simulator, and for quantum info, and here we can see that all of them match relatively well, which goes to show that this method of first decomposing a density matrix into its spectral decomposition and then running circuits where we initialize them using the eigenvectors of that decomposition and then sampling them using the eigenvalues of the decomposition can give us an evolution of a density matrix through real hardware. So I hope this was insightful, and as always, let me know if you have any questions.